Yeah, Gabriela, thank you very much for joining us today. We are very happy to have a talk straight from Brazil. Yeah, I was in Brazil, what was it, a month ago, 4 or 5 weeks ago, at a conference, and I met Gabriela there, and we discovered that we have some common interests, and then she started engaging with Donovan, and hopefully something very useful will come out of it. Yeah? And today, Gabriela will present some of her latest results about support vector machines and HHL. So Gabriela, thank you very much for being with us. You are welcome to start.
Okay, so first, thank you for the invitation. My name is Gabriela Pinheiro. I am a master's student at Universidade Federal Fluminense, or I like to call it UF, here at Brazil on Rio de Janeiro. And today I'll talk a little bit about the SVM generation using an optimized HHL quantum algorithm. So just a initial table of contents. Start by giving a little explanation of what it is a SVM, followed by a brief contextualization of the current scenario from computing, followed by the HHL algorithm itself, and then finishing with the results from two different datasets that we implemented this technique, and finishing with the conclusion and possible future works from it. So to begin, what it is an SVM? A SVM, or a support vector machine, is one of the main machine learning algorithm for binary classification. And binary classification is basically when you have a group of elements and you have to characterize it between two possible outcomes. A simple example, you have a group of patients and you want to classify either if they have a disease or not. And the SVM algorithms works as such. The data on those data set are mapped into points on a hyperspace. Here in this image, I hope you see my mouse. We have an example of a two-dimensional hyperspace where the blue points represents elements from one class and the green points from elements from the other class. And the goal of the algorithm is to find a hyperplane that will separate both of the classes, maintaining the biggest distance possible. Here in the image represented by this red line. And now if any new data point is inserted to the dataset, you can verify its class by its relative position to the line. In this case, if it is above the red line, it's blue. If it's under, it's green. Traditionally, finding this hyperplane is a problem with quadratic complexity. And because of that, it was applied a minimal square formulation to the original problem and turned into a linear system. That idea, specifically, it's completely classical. This wasn't done with quantum in mind, but this particular system, linear system, was already implemented with quantum in mind, with the use of the HHL in mind. Going a little bit about what every letter means in this linear system. The ones are just a line and a vector, line and column vectors with the number one repeated several times. K represents the kernel matrix, which is where the data information will be inserted on the linear system. And each element of the kernel matrix is calculated using this dot product function. And this is where all of the data information will be stored. This gamma here is just a user inserted error rate. And Y represents what we call as the class vector, which in the binary case is always, going back to the previous example, one class will be mapped as 1 and one is -1. In this case, the blue ones are the 1 class and the green one is the -1 class. So will be a vector filled with 1 and -1s, representing the classes of those elements on the kernel matrix. And then the variables of this linear system now are the parameter B, which is a real number, and the vector A, which is a vector of also real numbers. And the hyperplane will be defined using those variables. And the classification of a new data point, it will be done by this equation here, where if the value of this equation is positive, the class will be 1. If it is negative, the class will be -1, which is exactly the process of relative position. So the idea here is, now that we turn into a linear system, is trying to find better methods to solve this linear system. And one of them being with the use of quantum computing. Just a really brief contextualization of the current era. The quantum computing is a computational field that aims to use quantum mechanics to solve some problems better than classical computers. We cannot solve all the problems, but specific problems we can solve it better. But we are, however, in a still growing phase of this technology, this field. So we don't have already really big quantum computers with fault tolerant bigger computers available. What we have available are only the noise intermediate scale quantum computers, the NISQ quantum computer, which is also the name of the current era of the computing. And they are computers that are a little bit bigger. They go over 100 qubits, but they still have a lot of influence from the noise. And with the noise influence being directly proportional to the size and depth, a characteristic from the current era is that smaller circuits tend to suffer with less noise interference, which is pretty simple to understand. Like the smaller the circuit, the less chance will be the measurement will be affected by the noise. So currently on the NISQ era, the smaller we can get the circuit, the better. And in practice, as a sum up, the current era allows us for the implementation of efficient quantum algorithms, but we still need to keep it on a relatively small scale. One of those efficient algorithms being the HHL. It received name after its creator, its authors, Piero Hessedin and Lloyd, and it's a quantum algorithm for the resolution of linear systems. It does not, however, return the exact solution of the system. What it does return is the ratio between its elements in an efficient way. On the original paper proposing the HHL, it not enter into much details about implementation. So this algorithm is expected to reach exponential speedup in comparison to classical algorithms, but we are still not able to build circuits that reach the exponential speedup yet. So it is back in the future, but still today is one of the open problems with the HHL is to build a circuit that managed to achieve the exponential speedup. And the idea here, it's pretty simple, using the HHL to solve the SVM linear system. And that idea was previously used on the literature. As I said, that circuit system specifically was proposed with the HHL in mind. And in one of those implementations, Young and one of Alcera managed to have successful results by fixing the B parameter as 0. And fixing the B parameter as 0 has some consequence on the linear system. The first one, we can remove a line and a column from the system, because when you multiply it by 0, the result will always be 0. So we can remove it from the system size, reducing its size. Also, if B is 0, now the hyperplane will necessarily cross the origin of the hyperspace. So the 0, 0 and the 2 by will be a part of the hyperplane. And the last one, and most important for the HHL scenario, is that without the parameter B, the only remaining variable is a vector A, which means that we no longer need the exact solution of the system. If we have the ratio between the elements of A, we can already trace its inclination and consequentially find the hyperplane, which is exactly what the HHL can do efficiently, turning to the perfect scenario for the algorithm application. And because of that reason, that was the system used through all of the experiment. So it's just literally the same circuit without a line and a column. So it's a simplified version of it. Now, talking a little bit about the quantum circuit of the HHL, how to build this quantum circuit. We have here a smaller image, but after I have the bigger version of it. So the circuit for HHL has 3 different registers. The first one is the Insula register, which has only a single Insula qubit. The K register, where the coronal matrix will be stored, and it has the dimension, what we call is NK, which is a number that I will explain further how to calculate it, but it is the most unpredictable part. So in reality, what it means is the precision needed to represent the coronal matrix. So this number can vary more than the other ones. And I'll talk a little bit later how to calculate this number. And the last register is the Y register, which is the register where the vector Y and the final answer will be stored. And it always have NY qubits, which is always the log of the SVM dimensional. So a 2-dimensional SVM will need 1 qubit to be represented, a 4-dimensional 2 qubits, and so forth. So the circuit will always have a size of log n plus 1 plus nk. That it is where the circuit can grow more unpredictably. Not unpredictably, but more variational. So going to each step of the circuit creation, we start by the mapping of the class vector. In a generic case, you need to apply a traditional state preparation, a quantum algorithm, well known, which is and also is considered one of the bottlenecks of the HHL algorithm, because you cannot reach the exponential speedup with implementing the state preparation. In this case, however, because we have a fixed structure for the y vector that we can manipulate it, we are able to efficiently map the circuit to a known quantum state. Here, I'll explain a little bit later. The y vector we can always manage for it to always have a 1 and a -1 structure. So there will be a 1 followed by a -1, followed by a 1, followed by a -1. That when we normalize it, it have this shape here, which is maybe is already recognizable as a known quantum state, which is the minus state. Here I have an equation showing how you get to this state and how simple it is, because you only need to apply a knot on all the qubits, followed by Haldor mark. And when you do that, you end up with this state here, that when you turn it from the direct notation to the vector, it goes back to being exactly the normalized y vector, meaning that we are able to efficiently map it with only a complexity of the log of the dimensional of the SVM. So we managed to implement it with the logarithm complexity, because it becomes known as the minus state in compute. Just a disclaimer, the HHL algorithm itself does not consider the mapping of the y vector as part of the algorithm. It is considered a pre-requirement. So you need to do a mapping of y vector, but the HHL does not consider it part of the algorithm itself. So it's a requirement. And now we are technically entering the HHL algorithm itself. And it starts with a quantum phase estimation, or QPE, which is a well-known quantum algorithm that is originally intended to be an eigenvalue estimator and is used to map the kernel matrix into the circuit. And that is the second bottleneck of the HHL algorithm, because currently today, we just do not have an efficient way to implement a generalized QPE circuit. And it's still an open problem that it stops us from reaching the exponential speedup yet. The QPE worked as such. We start with a superposition of the empty bits with the Haldor gate, followed by a control unitary operator, and finish with the inverse TFT, which is a quantum Fourier transform. It's also a famous dataset quantum operator that I'm not gonna dive into details, because there are a lot of pre-made implementation of it available. And now if we head to the parts to calculate the NK number, because the NK number is related to the unitary. To calculate a unitary, we have the concept, or we call it a lambda dash, which is each lambda is the eigenvalue of the kernel matrix. So each j, the jth eigenvalue will have a lambda dash j. And the lambda dash are calculated by dividing all of the eigenvalues by the minimum eigenvalue and getting the round number of it. So it's a integer division. And we do as such to first have only integer numbers to work with, and second, so that we have the ratio between the element with the integer ratio between all of the eigenvalues. And nk will be the number of bits necessary to binary represent all of those numbers. So in practice is the seal of the log of the maximum lambda dash, because all of those lambda dash will need to be represented as the binary version of them. So nk is just the number of qubits required to implement the binary version of this algorithm. And that's why it's the more unpredictable part of the system, because the The precision may vary from matrix to matrix, so the size of circuit may vary from case to case. And their lambda dash are used to calculate the unitary operator. Here we have all the lambda dash, and you have a U operator with U diagonal operator that can also be called a U to the 2 to the 0 operator. And each qubit of NK will have a unitary operator associated with it. So the 0, 1 will have the U diagonal. The NK qubit will have the U to the 2 to the NK, that unitary operator. So each of unitary will be controlled by a single qubit. And we use those unitary operators, diagonal unitary operation, to create the actual unitary operator that we calculated by using the U diagonals multiplied by the eigenvector times the transpose conjugate of each eigenvector. Now, after the TPE, we go to the second part of the algorithm, which is the control rotations on the ancilla qubit. There are mode control rotation on the ancilla qubit, and each eigenvalue will have a rotation associated. So we'll have n rotation, considering n the dimension of the SVM. It uses the RY gate, which is base gate for the computing. The theta is calculated by 2 times the arcsin of lambda dash, 1 over lambda dash, and the control state will be the binary representation of said lambda dash. To better explain this case, I brought here an example because I think it's easier to understand with the practical example. So here we have an example where lambda dash equals to 2. So the theta will be 2 to the arcsin of 0.5, which is a third of pi. And the binary form of 2, it's 1, 0. So we'll have a 1, 0 represented on the controls of Y gate. Here, this white circle represents what we call an open control, which is a qubit controlled by the 0 state. And here we have the black circle represents a closed control, which is a state controlled by is qubit controlled by the 1 state. So here we have the least significant gate being controlled by the 0, and the most significant qubit being controlled by the 1, represented the 1, 0. In this case, the number of NK was the same as the qubits necessary to represent 2, but it cannot be the case always. Usually it's not. But what you can do is just keep adding zeros to the left until you reach the precision size required. So now going to the optimization part of the algorithm. This optimization was proposed by Lee et al. And works exactly on the concept to reduce the circuit size using what we call a fixed eigenmeans. That in practice is a pretty simple concept. A fixed eigenmeans are digits shared with the same value shared by all eigenvalues. So when you you represent the binary representation of all of the lambda dash, and if in the same position all of the numbers have a 1 or a 0 value, this is called a fixed eigenmeans. Here I also had another example that I think it's easier to see the concept. So here we go back to the lambda dash 2, and the second case here we have the lambda dash equals to 3. As you can see here, now the both controls are 1 because it's the 1, 1 number, and the least significant digits are different, but the most significant digit is the same value for all of them. It's always 1. So this is considered a fixed eigenmean. And the concept of optimization is that you can remove every fixed eigenmean from the circuit without losing its correctness. So this circuit becomes that one here with a smaller qubit, and which is really interesting because when you remove the qubit from the circuit, you also remove all of the operators that were associated with it, with being the unitary operation and all of the other unitaries on the key. So you reduce the qubit size and also the size and depth of the circuit with the concept. So it's a pretty simple concept of optimization, but actually presents really good results, as I'll show on the end of this presentation. So after the rotations, we go back to the final part with the inverse TPE, or the computation, where the kernel matrix information will be removed from the K register. And it, as the name says, just the inverse version of the TPE. So now we apply the TFT, the normal TFT, we call it U dagger, and the finish by the other one. And the U dagger is also calculated using the inverse of the U operator, the U diagonal operators. And then here we have an image with the complete circuit. As you can see, all of the phases, starting with the mapping of the Y vector, followed by the phase estimation and the control rotations, and the inverse phase estimation. To finish with the measurement, where in this case, we only measure two registers. The insula register will always have the value of 1, and the Y register, which will contain the A vector we were looking for. Now, having said explaining all the circuits and how we create the circuit, we go into some results where we tested on actual data sets. So for the implementation, we use the Python language and the Qiskit library. And for each test case, we generated 3 types of SVMs. What we call a classical SVM with the exact solution of the linear system to serve as a baseline to what we was supposed to expect from those SVMs, a simulation one, which was from a noiseless simulation of the quantum circuit that worked in order for us to better understand how it would behave on an ideal scenario, and a quantum or quantum real device, which were from execution on real IBM quantum device. For all execution, we used the IBM Sherbrooke, a 128 qubits quantum computer. So we have separated here in 2 different examples. The first one being the diagnostic Wisconsin breast cancer database. This example is a little bit older than the other one, so it does not have the optimization in it. But I thought it was interesting to bring here just because it has a interesting study on the behavior. We have a how interesting the behavior are on the computer. So this example does not have the optimization, but the next one will have. So this concept breast cancer dataset is a dataset created from image of tumors on the breast region, but the dataset itself does not contain the raw image. What happened is from each sample went to a post-processing, and it is represented by 30 continuous features on the dataset. And it's not feasible to implement an SVM with all the 30 continuous features in the current state of quantum computing. So we need to do a feature selection process. And in this case specifically, we chose to only do 2-dimensional SVM. In that case, we have a bigger SVM. And to do that process, we used a brute force method because there were only 2x2 matrix linear system where all of the classical SVMs were generated for all the possible pairs, and the 3 ones with the best accuracy were chosen to go further with simulating and being executed with quantum device, being further tested. Here I just have an image with all of the possible combinations. And the training and testing process was made using the dataset. Elements were separated on 369 elements to the training and 200 for the test sets. The kernel matrix were generated using the feature average of each class, and the features were normalized in order to improve the quality of the results. And for each circuit execution, 10,000 measurements were performed. Now I'm going through the test results. We evaluated on 5 different metrics, which are accuracy, F1 score, precision, and recall. Here we have the first case, which was the worst performing one, but it's interesting to see that the simulation SVM had a small variation on it, where here is the box plot is almost a straight line. Here that has variation, but it's really small plot. And just to explain, we use it 5 case different. We generated 5 different SVMs for each case. We need to restrain to only 5 because of the limit on the free plan on HHL Quantum. We only have 10 minutes of execution per month, so we needed to keep the test size short. So here on the, you can see on the simulation that even though they underperform the classical, they have small variation, and the value is still close to the classical one, where both of them were able to reach over 90%. Just having the more variation on the recall and precision methods. Here we have the second case, and here is where the quantum SVM start to be better than the classical one. Here on the simulation, with the simulation SVM, both the accuracy and the F1 score was equal or better than the classical from the majority of cases, with the execution on a real device having a little bit more variation, which is expected because of the noise influence. And here we have the last one, which is the best case scenario, where the execution on a real device managed to be equal or above the median of the simulation SVM, and in the majority of the cases for accuracy and F1 score, showing that even though we have execution affected by the noise, we are actually already able to have decent results. We have results close to what is expected, even with the noise influencing. So we had more variation, but it's still, the box plots are relatively small when you are already able to have results really close to what we expected, even considering the F1 score, they are really close to accuracy score, showing that even though we have the noise influences, we are already being able to have usable results from executing on real quantum computers. The last example and the main example of this presentation is using the high time resolution University 2, which it was a data set created from pulsar candidates obtained from that survey performed by the Parkes Observatory in Australia. And the RTRU2 is composed of 17,898 elements, each element being represented by 8 computer features. And that's a really interesting feature about this SVM generation method, is because the kernel matrix is not directly influenced by the size of the data set, we are able to use a large data set on the quantum circuit without actually having a direct impact on the circuit side, because the size of the data set does not directly impact the kernel matrix. What impact is the range of its eigenvalues. So would allow us to use the whole data set to be tested, which is a problem with a lot of current quantum machine learning methods. Today, a lot of quantum machine learning methods are still restricted to small data sets, needing to go to process of undersample and or similar reduction process, where in our case, we can just use the full data set without losing any efficiency. But we are still limited on the qubit size because we wanted to have the same analysis from the comparison between a simulation and a real device. And the basic simulator provided by the QSUN has a limit of only 24 qubits. So even though the quantum computer go to 128, the qubits on the simulator are limited to 24. So we needed to the limit to this qubit size, circuit size, and because of that, we weren't able to use all of the 8 features on a single circuit, meaning that we also needed to go through a feature selection process. And we managed to do a pretty similar process than previous case, where we tested all of 2-dimensional and 4-dimensional SVMs, and the one with the better accuracy were chosen to go forward with the testing. And here we have a table with all of those SVMs and the features used in each case. and the IDs that we're going to use to reference them from now forward. And here we already have a really interesting part, is that the difference on the qubits, the number of qubits on the original circuit and the optimized circuit. So in all of the cases, we managed to reduce the circuit, and going further into this 24 qubit one was the best case, where we managed to reduce on 10 qubits from the original circuit. So showing that even though it's the simple concept of optimization, it does have a considerable impact on the circuit. Here we have the five circuits, 5 qubits, 10 qubit plus. So it does have an impactful reduction on the circuit. The training test process was basically the same as the previous case, but the difference that the data was randomly split within a 30-70 ratio into training test set. When we're also using 10,000 measured for execution. So we go into the results from those cases where we compare the SVM with the classical and SVMs from the regional and optimized circuit. The initial test is just to see the efficiency of said SVM. And this here has a really interesting result where both quantum computers managed to both SVMs generated from simulation and real device managed to have a pretty close result from the classical, with the averaging on 25%, 25.41% on the best case, and 26.16 on the best case on the real device. For simulation, we use the average accuracy of 20 simulations for each circuit. On a real device, we only managed to use the average of 2 executions, again, for the same 10-minute limit problem. And here it's really interesting to see that on the simulation scenario, the optimized circuit presented a better average on every single case tested. And on a real device, we actually lose it in only a single case, which was ironically the best SVM of all of the quantum ones. But in all of the other cases, we are either tied or was better than the original devices, which is really interesting to see because we managed to have better results on a smaller circuit. So it's a win-win situation. We reduce the circuit size and still managed to get a better accuracy than the original circuits. Another way to analyze the impact of the optimization is testing the execution speedup. And for me personally, is where I think the optimization shines the most, is it managed to significantly reduce the execution time for its circuit. So we also use the average of all of those cases before. So every time we're going to talk about time here, is always using the average. And the creation, and in the best case scenario here, the creation time went from 22,000 seconds and the execution time to almost 1,000 seconds, which if you combine the creation execution time for this SVM specific, it goes over an hour. To when we optimize it, it went from over an hour to under 5 seconds. So it was 1,000 times, more than 1,000 times speed up execution time. On the other cases, was less drastically, but you still have really good ones. Here on the second one with the 4-dimensional, went to 200 seconds to only 10 seconds. And this also is really interesting because the bigger the secret you have, the more the reduction will impact. Because on the two-dimensional SVM, they have a small number of qubits. So even though they have an optimization, the reduction, it wasn't as impactful as on the bigger circuit that it became really, really noticeable. And when we look into the real device, the speed up was less drastically, but considering that the payment method for quantum computers on IBM and also on Amazon bracket, there's also a way of doing like that is by the time of execution. So in IBM, the payment method, the charging method is based on the time you spend executing a circuit. Every second we can remove from it, it's money that we're saving. So here in this case, we managed to go close to a half of the time. So it's basically half of the money that we managed to remove it. So even though it was less impactful, it's still we're directly saving money. Another way to analyze this impact is by looking the circuit depth and size. We use here the concept by the Christic concept of depth and size. So the depth of the circuit is the biggest sequence of operators needed to be measured in sequence. And the reduction of the depth is really important when you consider the noise, because the bigger the depth of the circuit, the longer it needs to be isolated. And the longer the isolation of the circuit is a hard processing, and the longer you need to isolate it, the more likely it is that will be affected by the noise. And this change in depth and size is really important when you consider the transpilation process, because when you first think of it, it looks like you're not removed a lot of qubits from a lot of operators from a single reduction. But when you consider that the circuit needs to be transpiled to be simulated and executed, and the transpilation process is where you take a circuit and transform it in, and you translate it to only use a set of operators available on said simulator or real quantum computer, that can be a real way more impactful. Here, again, being on the bigger case, where a circuit that theoretically only have 53, the depth of 53 operators, when you went to simulate it, it actually turned into 6,000 operators, and execution on a real device went to 30,000 operators. So it can grow really significantly. Each operator that you remove, you can have a really big impact on. In this case here, it went from 6,000 to under 3,000. So we managed to cut in by half. And here we went from 30,000 to 13,000. So it's a real more also close to the half of the original size. The idea is pretty similar with the secret size. The concept of secret size here is just the total number of operators, which again is the same idea. The more operators you have, the more likely they will be affected by the noise. So the smaller the operator, the more noise resistant the circuit possibly is. And again, here we also have an even bigger impact on the numbers. So it went to 7,000 operators here to only 3,000 over half. And here is a really interesting case as well that went from 61,000 operators to just under 25,000 operators, showing that if it's simple optimization like that, it can have a huge impact on the depth and size of the circuit. And now we go on to the conclusion of virtual works of this work. So we started by presenting a circuit generation method for SVMs using an optimized digital algorithm, and obtaining possible results on a real quantum computer demonstrates that it is actually viable to use the method with the current available devices. So we managed to get coherent example. We actually managed on the pulsar, actually the best quantum result came from, best quantum accuracy came from a execution on a real quantum device, showing that it is possible to use with what are currently available for us. And also, the consistent results obtained from the quantum method could indicate a possible advantage from quantum over classical computation in this case, because if you have similar results more efficiently, you can consider this an advantage. And again, because this data set size does not directly interfere with the circuit size, this method can be applied to large data sets, which is really interesting considering that majority of the quantum machine learning algorithms are not able to be applied to large data sets. And now thinking about the optimization itself, the average accuracies obtained by the optimized circuits indicate an improvement overall from the original algorithm, because we are able to obtain better results with significant smaller results. As I said, it's a win-win situation where they were smaller and better. And also the execution speedup obtained allows for the more time efficient SVM generation pipeline, because now the time when you would spend generating one SVM, now you can have more than 10 SVMs depending on the case. And also can indicate a more noise resistance. Again, because the circuit is smaller, they will less likely to be affected by the noise than the original ones. And for future works, an idea is to expand the use cases for a larger data set in order to test its performance on more realistic scenario. Is one of the projects that I'm currently working with Donovan and Professor Petruccioni, that we are trying on a more than a gigabyte data set to see how it works. We are still not in the testing phase of the quantum techniques, but for our classical looking, maybe feasible to use it on that said data set. And also search for an efficient generalized QPE circuit and another optimization techniques for the HHL circuit in order to try and reach the expected quantum advantage, which for now is still an upper problem. The QPE is not efficient enough to be considering reaching this expected quantum advantage. And that's it. Thank you so much for listening. And do you have any question or something?
Thank you very much, Gabriela. Very nice presentation. Do you have questions and comments for Gabriela? You should have.
I think there are two things that I just need some clarification on. One has to do with the precision that you need. A certain amount of qubits corresponds to a certain precision. Can you just explain that again, please?
Yes. So what we do have here is, let me go back to this slide. We have this unitary operators, and what we do here, we map those unitary operations and to the NK bits to be binary represented, and for the rotation here. So what we do need to do is have a expected precision to represent those values. We don't need to represent the original value of the eigenvalues. That's why we have this, what I called a lambda dash transformation here, because what we do here, we divided every eigenvalue divide every eigenvalue by the minimal, because on that way we have the ratio between all of those elements. So we have this 2 times bigger, 3 times bigger, and then we round it to the integer. We do an integer division of this data, which also we kind of lose a little bit of data here, but it's something that is part of the circuit. So when you have those integer value, you only have integer values, you will need to represent them on the circuit. And the precision will be the number of qubits required to represent all of those various binaries, because here on the rotation, we need to represent them on the circuit as binary versions of this control. So you need to calculate the precision is calculated by that, the number of bits you need to represent those values. So in this case, if example it was 2 and 3, you only needed 2 qubits to represent it on the region circuit. So, and the optimized version, what we do is we calculate all the lambda dashes, and after going up the dash, we check for the fixed eigenmeans and reduce from the original NK. So, but this is how we calculate the precision. We see all of the lambda dash that we're gonna use it and see how many qubits is necessary to binary represent. Did it answer your question, or?
I think so, yeah. I might have to read your paper again and again just to make sure I truly understand. I can't get let me just check. There was one more thing somewhere.
Anybody else has questions where a lot of things? No, Adrian, do you have suggestions? And Gabriela, what bigger data sets were you thinking of using?
So currently has the data set of the project that we're working, which is another astronomical one with there's a 1 gigabyte version and the 16 gigabyte version of it. And right now I'm currently working with that one, because what I'm doing, I forgot to mention, is that I'm actually redoing all of those tests on the pulsar data set. So I'm currently doing some better tests to match more of the Wisconsin version, but testing more metrics and with more examples here because now I have a little more time to run it. So I'm running again to have more examples to have better accuracy. So what I'm currently working on now is to redo the pulsar test to have a better, redoing the test to have a better analysis of the performance, and at the same time using this another astronomical data set. So this is what I'm currently working right now. I'm focusing on those two data sets, and after I will looking for another type of bigger data sets to work with.
Nice, thank you.
Okay, so there was a question regarding the dimension of the support vector. When you say two-dimensional support vector machine and a four-dimensional support vector machine, what exactly do you mean by that?
So they are support vectors with using 4 features or 2 features to create the data. So, and it's two-dimensional as the linear algebra concept of dimensional as well. Here on the original image, the two-dimensional is, this would represent a two-dimensional. You have one dimension here and the second dimension here to test the data. 4-dimensional, you have 4 features to test the data. So that's the idea of a two-dimensional 4-dimension, is then a number of features used to calculate this data set.
Yeah, I was just making sure I wasn't misunderstanding that. And just one last comment, since you're doing more tests on the pulsar stuff, what would be really interesting to see is if you use precision and recall for the pulsar stuff as well, see how that changes from non-optimized to optimized.
Yes, that's the exactly the idea. That's exactly the idea. I'm running more tests to analyze all of those metrics because it was actually really interesting going to the Wisconsin. I didn't get into much detail to don't take a long time, but here on the Wisconsin here, as you can see, this case specific is really interesting because it was super precise, even better precision than the classical one, but had a terrible recall. So that's my plan, go into the pulsar with the different metrics to see how it behaves with the pulsar dataset, because we have a really interesting behavior on the precision recall, because here you can see there is a really good, considerably good accuracy and F1 score, but when you go to the recall and the precision, you see there is a way bigger range of values founded on those metrics.
Yeah, because what I typically have observed is that precision for my stuff at least, precision tends to be lower and recall tends to be higher. So it's just interesting.
Yes, makes sense because the embellishment of the data, because that was actually something that I didn't enter in much detail, because personally on this case it's not a problem, the data set is being imbalanced because I treat them as separate classes, but the pulsar data set is pretty imbalanced, so it's interesting to see this metric exactly because of that, to see how each class behaves.
Any other questions? Yeah. Okay, Gabriela, thank you very much. There doesn't seem to be any other question. I know that we will meet again next week, and I hope I will be able to join you next week.
We'll give you a nice rundown.
Yeah, no, perfect. That's excellent. No, thank you very much. And Gabriela,
Thank you so much.
Thank you so much for your time, and I hope you didn't have to wake up too early this morning.
No, it was fine. It's almost 10 a.m. for me. It's not that early.
Okay, it's not so bad, not so bad. Yeah, excellent. Wonderful. Thank you very much, Gabriela. Have a nice weekend.
So
Thank
much.
you. All the best.
Bye. Have a nice weekend, guys.
Bye-bye. Bye. Thank you.